Hey everyone, thank you for connecting and watching our presentation today. We came here to actually hear and see interesting presentation about today's topic, which is interpretable neural network for panel data analysis in economics. And this topic is interesting definitely because if you have never come around cross-sectional data or panel data, you will definitely learn a lot. And also we will see interpretable functions incorporated in neural network architecture. My name is Jiri, and I'm a stream owner of machine learning in economics, and I focus in AI solution capturing human behavior through cognitive sciences and machine learning. Today, I am very honored to have Yucheng presenting today. Yucheng is a 4-year PhD student at Princeton University, and he studies big data and high dimensional model in economics. Just prior to this talk, Yucheng shared with me that his newest publication is Knowledge Graph for Microeconomic Analysis with alternative big data, and he will actually be presenting that for Federal Reserve. Also, let me to briefly introduce AISC. AISC, or our group, Aggregate Intellect Socratic Circles, is a community of machine learning practitioners and researchers who have gathered around 3 topics in AI, which is research, engineering, and products. We host 3 live sessions like this 3 to 5 times a week and produce premium content in various subject areas. To see more, please visit our website, ai.science, and log in to access slides from this and other sessions and many more. Please make sure you subscribe to our YouTube channel, ML Paper Explained, to get notified about all the live sessions and other free content we publish. We currently have about 15 different streams that are focused on various machine learning topics, and this session is machine learning in economics stream. Hope you enjoy it and come back. So I already mentioned that we will talk about cross-sectional or so-called panel data and interpretable functions. And actually, this week I happened to be on a call with my friend who is an economist at a large financial advisory company that conducts economic research regarding risk and performance and financial modeling. And we were talking about how they are actually limited using standard statistical models that are limited to linear and logistic regressions, mostly because interpretability is the large issue, and that limits economics from using more robust and better performing models, which on the other hand are not so interpretable. Today, Yucheng will present his interesting research that composes a neural network architecture that is robust to missing data. And what I specifically like about this work, that it's interpretable at first place, and it expands the toolbox of interpretable models in economics as whole. So please welcome Yucheng, and I'm passing you my word. Thank you.
Okay, thank you very much, Yuri. So can you hear me now?
Yes, I hear you well.
Okay, great. So thank you very much for having me here today. So today I'm going to present my work on interpretable neural networks for panel data analysis in economics. So I'm Yucheng Yang from Princeton, and this is joint work with Zhongzhen from Penn State University and Professor Weinan Yi from Princeton. So as Yuri mentioned just now, so many economists nowadays are using more and more big data. But as you can see from many of those big data papers in economics, so most people are still using simple models to study big data. So it's kind of puzzling to people that why economists not using advanced tools like neural networks. So the main reason that people have been talking about is a lack of interpretability and transparency of conventional neural networks, which people usually refer as a black box. So in this paper, we propose a new class of interpretable neural networks to study panel data, which is commonly seen in economics. So our model is kind of a compromise of conventional neural network models and the simple interpretable functions like linear or logistic regression functions. So the model shares similar multi-layer architecture with conventional neural networks, which start with interpretable functions in the first several layers with some unknown parameters that we hope to learn from the data. But in the final layer of this new model, we regularize the final layer so that the model can be written as a simple function of a limited number of interpretable features. So to help you understand this comparison better, so let's look at this visualized comparison between conventional and interpretable neural network. So on the left-hand side, this is a conventional neural network you see in many of the recent papers in machine learning and AI. But on the right-hand side is an interpretable neural network we proposed in this paper. So as I say, so the first several layers of this new interpretable neural network is interpretable functions, which are encoded as part of the neural network. So all these circles in this layer will be interpretable features constructed from the original data. There will be a lot of these interpretable features, but we will not allow every of them to enter the final model. So instead, we will add some regularization when we train the model, so that only a small number of interpretable features will finally enter the model. So that the final model can essentially be written as a simple function, which is here a simple function of a regularized number of interpretable features, like these red circles. So those interpretable features, they are outcomes of the interpretable functions encoded in the neural network. So this is the general idea of this interpretable neural network. So before presenting the general formulation mathematically, so we may want to talk about one thing. So that is what is a interpretable model. So this is actually a very hot topic in many of the recent literature. So instead of proposing something new about what is an interpretable model, we will quote this paper by Professor Bing Yu's group at UC Berkeley. This paper is published in PNAS last year. So the paper proposed 3 key elements of a interpretable machine learning model. So the first element is what they call as predictive accuracy. So which means that a interpretable model, at the first place, it should be a good model. So a good model will fit data well. So that's the first thing about predictive accuracy. So the second element is so-called descriptive accuracy, which means that we can kind of describe the model with some interpretations. So in their paper, they make an example of an uninterpreted model, which is conventional neural network. Because there is so many layers and so many interactions in conventional neural networks, it will make people very hard. It makes it very hard for people to describe the model itself. So the model should not be complicated. That's a kind of that's a requirement for an interpreted model. And last thing is what they call as relevancy, which means that the model should provide some insights or knowledge for the domain or task you study. So I will say this relevancy requirement will be very domain specific, which means that when you study a different problem, so an interpreted model will be very different. So for example, when you study computer vision problem, so what is interpretable model will definitely be very different from a problem in economics. So this paper, in this paper, our interpretable neural network will meet all these 3 requirements. So So first, our model will have high predictive accuracy because it is kind of a variance of neural network. You'll fit data well. So the second thing is that so as I said earlier, we specifically design the model in that way so that it can be written as a simple function of a living number of interpretable features, which makes it has high descriptive accuracy. So the last part about the relevancy falls in the interpretable function of our interpretable function part of our model. So actually, people can design different interpretable functions based on the nature of different domain tasks. And in this paper, so we are designing a class of interpretable function for panel data study. So as I say, in this paper, we will encode a class of interpretable function called persistent change filter, which I will explore a little bit more later as part of this neural network. So we apply this model to study individuals' monthly employment status, use administrative data in China. So we'll achieve, as I show later, we'll achieve high accuracy, which is close to the best performed conventional machine learning methods, which may not be interpretable. Also, we can clearly understand how the model predicts individuals' employment status. So as I will show later, so our model's interpretation will be qualitatively similar to those worst performing logistic regression models, and it will be very robust to data missing problems. So for the sake of time, I'm not gonna dig into the literature very deeply. So, but if you have any questions, so please feel free to put in the chat box so we can talk about this later. So, so before going to panel data, let me present the general formulation for a interpretable neural network. So, so as is similar to a conventional neural network, so this model is also have a multi-layer kind of structure. So, and the first several layers will be interpretable function with unknown parameters. So, and we can design different kind of interpretable function based on the nature of different tasks. And the important thing is about the final layer. So the final layer, in terms of functional form, it will be a linear or logistic function, but we will also add a penalty term into the loss function when we're training the model, so that the effective inputs for the final layer are required to be sparse. So this simple general formulation can be visualized in this way. So as you can see, so these are the first several layers which are interpretable functions, and so these functions can be designed based on the nature of your task. And for the final layer, it will be regularized so that only a small number of interpretable features can enter the final model. So I guess maybe we can take a pause on the presentation to see whether there are any questions coming from the chat.
Yeah, thank you for your thank you so far for your presentation. It's a very interesting work. Now I would like to ask the online audience to ask any clarification questions. I will ask Yucheng directly. Otherwise, I prepared some questions myself. So one interesting thing I see there is, and actually I forgot to mention it during the or while I was introducing or telling or saying what I specifically like on your paper, and it's the feature selection feature, which basically means that even out of 1,000 features, you can select the 10 most effective, right? The 10 most effective ones, right?
Yeah.
So, and my question was, how do you find this? Like, doesn't it make the model less, like, what's the trade-off between selecting the most effective feature and performance? do you find any like evidence that it makes the model less or more, the accuracy performing?
Yeah, so this is a good question. So actually, as I mentioned earlier, so for the basic, so some of the basic requirements for an interpreted model include the predictive accuracy and descriptive accuracy. So by restricting the effective number of interpretable features to enter the final model, we might sacrifice some degree of predictive accuracy, but will obviously make the model more descriptively accurate. So for example, if the model is a simple function of 1,000 interpretable features, and then you say that, which means that those 1,000 interpreted features will affect the final results, it will definitely be harder to interpret than a model of just 10 interpretable features. Yeah.
I see. Thanks for the answer. And can we go quickly back to the schema or the architecture?
You mean this one?
Yes. So and I'm looking at the red circles. Can we? So what are they? Are they neurons or layers?
So they are neurons in the final but last layer.
Yeah, I see. And then if I look at the GM-1 layer, there is a like, it seems that the black neuron is disconnected from the network. It's the interpretable function, isn't it?
So all these features are interpretable.
Yes.
But as I mentioned when I answer your question just now, so we cannot allow all these features to enter the final model, which will make the model too big. Mm-hmm. So we hope to kind of balance the predictive accuracy and the descriptive accuracy, mm-hmm. so that we'll only allow those red circles. So which actually they are essential equivalent to each other in this layer, but mm-hmm. We select those red circles to so that the model can be kind of smaller, but still maintain a good predictive accuracy.
Yeah, I see. Thank you for that. But maybe I express myself in a bad way. I'm looking at the neuron or layer like slightly left from the interpretable features. It seems that it is not connected with the previous layers.
Oh, you mean this one?
Yes, exactly. Is it just my impression?
Missing of arrows. So actually, I can put more arrows here. So
yeah,
I see. All the neurons are coming from are outcomes from previous layers.
I see.
Yeah, okay. Thanks for this clarification.
No worries. And then actually we may talk about it later after your final presentation. But I don't know what are the policies in China. But how difficult it would be to push like this approach for a general adoption in economics. For example, in predicting the unemployment rate.
So I guess so it will be a bit challenge to push this in academic research, because in research people, economists, they mostly look into causal inference problems. But actually in practice, so there had already been some attention on our paper whether it can help policy makers or consulting firms, whether this kind of method can help them to improve their policy making or firm decisions. There has already been some interest in that, and obviously, as you see, interpretable models is very important for economics, so that people can understand the mechanism behind the model. Yeah, just beyond just have a good predictive model.
Thanks for that. And also, I finally noticed that there are like I didn't keep an eye on the chat, but I noticed several questions from the online audience. So can I ask you, or Luz Zheng is asking whether is the feature selection important for the interpretability? And given that the first functions are interpretable, what does feature selection actually bring?
So, this question is relevant to the question you asked me at the beginning. So, this is just a trade-off between a very big model. So all the model inputs are interpretable, but it's very big. So, for example, I haven't presented yet. So we are gonna apply this model to do individuals' employment status prediction. So, for example, if you know that there is 1,000 individual features that can predict your employment status, it will kind of be be difficult for the policymaker or people who are interested in this issue to to control all these things or to design policy based on this kind of big interpretable model. But if there's only 10, or as I will show a bit later, like 7 or 6 interpretable features enter this final model, it will be easier for for policymakers or interested parties to understand the mechanism and also to make better decisions based on this kind of models.
Yeah, thanks. And I also see that we got a question about shared values, and I actually prepared this question, so I would ask Achilles to wait at the end of the presentation. We will definitely discuss that. And last question I would like I would like to ask here is whether what I just lost the question. Yeah, on what basis do you decide the number of neurons in interpretable layer?
So yeah, this is also a good question. So as I will show later, so I mentioned this briefly before, so that the interpretable function will be designed based on the nature of your task. So I will design an example of interpretable function based on when I study panel data. But if you study a different problem, like if you study, you study like asset pricing problems, if you study, default prediction problems, you may hope to design different, interpret functions, and the number of neurons will be relevant to the interpret function you hope to design.
Yeah. So it's a hyperparameter as in other, like number of the neurons is a hyperparameter as usual.
Yes. Yes.
Awesome. Yeah. Okay. Thank you.
So thanks for the question. So I guess now we are going more specifically into interpret the neural network for panel data. So we actually designed this 4-layer, interpret the neural network for when we study panel data. So the first layer is this decision tree type splitting, so which is essentially a sigmoid function. As you know, that the sigmoid function can operate to split a continuous variable into a 1, 0, 1 type of variables, which we call as decision tree type of splitting. And second layer is the dimension reduction. So which because usually when we study administrative data or computational data, so there's always a lot of very high dimensional data there. So we can have some dimension reductions. And the third layer is a class of interpret function called persistent change filter. So which I will spend some time talking about in the next few slides. So and I say earlier, the last layer will be a regularization on a simple function. So now let me jump into this class of interpret function we designed in this paper, which is called persistent change filter. So imagine for a time series for some individual I. So because in the panel data we have many individuals in a cross-section, and we have time series observation for each individual. So for a time series on some individual I, we skip the subscript I here. So the time series x tau, it's time series between 0 and 1. So this is kind of natural assumption because we know that we always do a lot of normalization to 0 and 1, and also because we have a lot of sigmoid functions, so which map everything between 0 and 1. So this is kind of a natural assumption. So we define this persistent change filter D on this time series. We define this persistent change filter as a difference of two time series, PT and QT. So both PT and QT are defined in the following recursive way. So the first element of PT is PT, which is P1, which equals to X1. And the first element of QT is equals to 1 minus X1. So for PT time series, it is defined in the following recursive way. So I will help you guys understand why we define this in this way. But now I'm gonna mention two things. So first is that there is some unknown parameter in the definition of persistent change filter, which is K. So this parameter we are gonna learn from the data when we train the interpreted neural network. And another thing that so with this persistent change filter, we'll map the original time series into a new time series. And I will show later that this new time series actually capture the duration of persistent changes in the original time series. So what is this persistent change filter? So as I say, it is defined as a difference between these two time series, PT and QT. So first let's look at the spatial case when we require the smoothing parameter K equals to 1. So as you can see, if K equals to 1, so this PT function will be written as K tau plus 1 P tau plus X tau plus 1. So you can write this recursive form into this non-recursive form for this formula PT. So if you are familiar with some time series trick, so this thing actually have some special meaning. So when the time series xt is a binary time series, so which says that the xt only takes two values along the way, either 0 or 1. So like xt is like this way. So if xt here is t here, and if this is t minus t0, so if this xt has this structure, so all the xt after this t minus t naught period is equals to 1. But we don't. But at this point, the value of this time series is 0. Then the PT will equals to T0. So the PT will essentially be the lasting time periods for the recent X taus, for the recent XTs to be equal to 1. So which kind of capture the persistent jump from 0 to 1 in this time series. So it captures the time period since the most recent jump from 0 to 1. So when xt is a binary time series, so this PT will capture this thing. So similarly, if we allow xt to be continuous between 0 and 1, so in the paper we show that PT also captures the recent persistent jumps. So here the jump just being a jump. It's not a jump in a continuous time. In a stochastic calculus setting, it's just a jump. So similarly, so we can define a QT. So as you can see, QT is kind of a opposite of xt between 0 and 1, because you see that at the first step Q1 is 1 minus x1, and you can see this kind of symmetry between the definition of Qt and PT. So which allows Qt actually captures persistent drops for continuous xt between 0 and 1. So to take the difference between PT and Qt, so this ZT, which is a persistent change filter we defined in this paper, will capture the persistent change pattern in the time series of xt. So yeah, so I guess, so this is the basic logic and also the motivation for us to define this persistent change filter. So now you may trust me that this persistent change filter is what really captures the persistent jump or persistent drop in a time series. So we also allow a trainable parameter k which falls between 0 and 1 to allow for some smoothing. So when we discuss everything here, we assume that this k equals to 1, which is correspond to no smoothing in this setting. So, but in the next slides, I'm going to show you that. So when there is some abnormal data problem or data missing problem, k less than 1 will be necessary. So let's look at so these two examples. So the first example is kind of a perfect binary time series. So all the data point is equals to 0 before this cap t minus t naught period, and all the time series after this cap t minus t naught period will be 1. So this is kind of the ideal persistent jump time series. And as you can see in this example, we plot the persistent change filter with different values of smoothing parameter k, which is equals to k, equals to 1, 0.75, 0.5, against this transition period t naught. As you see that, so we have the ones persist for t naught period, and we plot this persistent change filter against the choice of t naught, and we we find that so all these plots will fall onto a 45-degree line, so which is invariant to different choice of k. This is because this time series, this kind of perfect time series. But if we randomly set 10% of the data after this cap t minus t naught period to 0.9, which is kind of to mimic this abnormal data issue or missing data problem. So as you see, the original time series will look like this, which is very persistent. So, but the new time, this example 2 time series will be, so there will be a lot of ups and downs here. But we still should know that the persistent change actually happens here, right? So if we plot this persistent change filter with k equals to 1 against the transition period t naught, so it's still a monotone function, but it's very far away from the 45-degree line. But if we decrease the value of k, it will get more closer to the 45-degree line, and it will capture the persistent change transition period better. So this figure will may convince you that the choice of k kind of matters in this persistent change filter function. And also, I think both two figures can convince you that this persistent change filter really capture the duration of a persistent change. So now we are gonna use this 4-layer interpret neural network design to do some application work. So we are gonna use this interpretable neural network structure to predict individuals' employment status for a 4 million population city in China. So the output for this model will be binary, which is if it is 0, it will be so some individual is unemployed. If it is 1, which means some individual is employed at some period t. And we have a very high dimensional model input. So here we have the data for individuals' payment amounts for different types of insurances. So because we take this data from a administrative data set, so it mainly contains the payment records for individuals for different insurances, among other features. So we will stack the feature of individual in the past S period as model inputs. So if there is m, if there's m dimensional of input for a given time period, and we look at the past S period, so we will have a m times S dimensional, model input here. So which is actually makes the very, high dimensional input. And then we will use the interpret neural network structure we designed for panel data to study this problem. So, so besides running this interpretable neural network we designed, we also compare this our model with some other baseline model. The first comparison target is the kind of the best traditional interpreted model, which is logistic regression. You know that when we use logistic regression, you may not want to use the original data input, like the m times s dimensional input as a model input. You always need to do some handcraft feature engineering, and then we really work very hard to design different set of different set of features, so that the logistic regression model can also perform not too bad. So another comparison baseline is some other good performed but not the interpretable models that people always use. So which is random forest or neural networks models. So here we will so similarly we need to design those handcrafted features as model inputs for random forest or neural network to avoid too heavy model tuning. And here we report the model testing accuracy in the out of sample test set. So we actually surprisingly find, so first we find that our testing accuracy is dominates all these other interpreted models. So what makes us a little bit surprising that our testing accuracy is even better than conventional uninterpreted models like random forest or neural networks. So here we report the test accuracy. Here report the better performed testing accuracy for random forest and neural network here. So this is a bit surprising because which says that interpretable neural network may even beat conventional neural network in terms of predicting accuracy. So actually, at the beginning, we are also kind of surprised about that. But later, so we find this interesting paper which argues that interpretable features may have better accuracy in a test set than conventional models because they really capture some underlying logic of prediction. So you can refer to this interesting ICML paper which published this year for their argument. So which also say that it's not wrong or something like that. So we honestly report what's the testing accuracy on our data set. So beyond this predictive accuracy, so our interpretable neural network can also deliver a very clear mechanism of how this model really predict the individual's employment status. So as I say, so our model is a 4-layer model. The first one is a decision tree type of splitting, and second one is a allows for some dimension reduction work. So which here, so then the third layer is the persistent change filter, and the last layer is a simple logistic function, simple logistic function. And here, so we can look from the last layer to understand the how this model predict individuals' employment status. As you see, this sigmoid function has a coefficient very close to 1. So as many of you know, when a sigmoid function has a coefficient close to 1, it is actually very similar to an identical function, which essentially say that this YIT is prediction for employment status. We essentially predict this employment status using this outcome of persistent change filter, X3. So what is this persistent change filter function on? So it's function on this X2. So X2 is actually a composite variable from a linear combination of these X1s. And we will see what is X1. So here you see X1 is this outcome of this sigmoid function. And this sigmoid function has a very large negative intercept term. So which means that it will map this original xij tau into a kind of an indicator function, a binary function, for whether an individual pays or not pays some specific type of insurance. So with this understanding in mind about X1, we will know that, so we essentially predict the employment status with this persistent change filter on a composite variable. So the composite variable is a linear combination of whether an individual pay or not pay each type of insurance. Okay, so you might think a little bit about my explanation here about the thorough structure of this model. And so one thing that we haven't explained is about these weights of the linear combination in X2 in this function. So these weights of linear combination imply the relative importance of whether you pay or not pay each type of insurance when you predict the employment status for each individual. So for example, the first element corresponds to whether an individual pays or not pay the endowment insurance. So which means that if we control everything else, unchanged. So if an individual pay a lot of endowment insurances persistently before, but suddenly it becomes, it changes to not paying the endowment insurances persistently. So this will have a negative, prediction probability on whether he is still employed, which means that if you start to pay a lot of endowment insurance, but suddenly you do not pay it, we may tend to predict, so this individual get unemployed. So similar story can be told for other types of insurances in this model. So as I mentioned earlier, so we actually, so now we'll have kind of a stories tell about people's payment history about different types of insurance and how it relates to, how it relates to her employment status. So we can simply construct handcraft those features and throw them into a logistic regression to predict whether someone is employed or unemployed. And we interestingly find that these interpretations is actually similar to a logistic regression, what a logistic regression can deliver. But of course, our model, interpretable neural network model, achieve a much higher accuracy, when fit the data. And also the logistic regression is kind of, guided by the model results of our interpretable neural network. Okay, so one thing that we think that an interpretable model should satisfy is that an interpretable model should be stable. So in terms of both accuracy and interpretation. As you know, a neural network model is not, a conventional neural network model is not stable. So if you change the way you're tuning the parameters, you change the way you initialize the model, you sometimes get very different outcomes for the model in terms of its parameters. But here we find that when we randomly set 10% of the model and of the data features into 0 to mimic a data missing problem, we will get a qualitatively very similar model estimates, and also the accuracy comparison will be very similar as we presented before. So which kind of showed that the model accuracy and the model interpretation is very robust to data problem. And interesting, as you may see, when we have this data missing problem, the smoothing parameter, if you still remember it, in the persistent change filter, will decrease significantly. So when we have the original data, the smoothing parameter is very close to 1. So, but here when we have a data missing problem, the smoothing parameter will decreasing significantly. Okay, so now we are done with application. So to conclude, so in this paper we propose a general class of interpretable neural network models, which can be written as a simple function of a regularized number of interpretable features. So those interpretable features are outcomes from interpretable functions, which we design one example in the setting of panel data. And other researchers can design different forms of interpretable functions according to the nature of their own tasks. And then we encode a class of persistent change filter to study panel data in this paper. And we apply the model to predict individuals' monthly employment status with administrative data of high dimensional inputs. And the model is accurate, the model is interpretable, and the model is robust to data problems. So as I mentioned earlier, so this general form of interpretable neural network has many potential applications if people can design different interpretable functional forms in their own tasks. So we are actually working on a few applications of this general framework in problems in like asset pricing, among others. And we believe that other people may design different forms of interpretable functions to solve their own problems. And thank you very much for your attention. So now I'm happy to take questions from Yuri or from the chat.
Amazing. Thank you, Yucheng, a lot. Great work. So everyone who has been watching us, feel free to ask questions in the chat. I will ask them Yucheng directly. Yucheng, just out of curiosity, how long did it take you to publish this paper?
We don't know. So because the paper hasn't been published, we just posted on SSRN archive, I think in October. Yeah. But we actually started working on this, I think 2 years ago. So when we get the chance to study the nice administrative data on insurance payment, among other features containing that data.
I see. Yeah, amazing work. So if I can ask you some questions, and we may have a discussion regarding that. So already during the first break, I got a question about the shape values, and for those who are not very familiar with this means, it's basically using other black box models in machine learning. There is a state-of-the-art post-hoc model in interpretable analysis, so-called shape values, that is done actually after modeling, and it shows how shuffling of features affects the model performance and magnitude of each feature. It actually comes from the game theory. So the question here was actually, if I can, what is the common ground between the shape values and your approach, and what may be the main difference here?
Okay, so this is a very important question, because so it's also relevant to the big literature on interpretable machine learning and the interpretable neural network. So So I will. So there is a very nice overview paper by Professor Bing Yu's group at UC Berkeley. So in their paper, they classify interpretable machine learning or neural network models into two classes. So the first one is called what they call as model-based models that deliver model-based interpretability. So the second class of interpretable model is those which deliver so-called post-hoc interpretability. So the model that deliver model-based interpretability is that, so okay, we design a model which is interpretable it's by itself, like linear regression. We don't really to look into the linear regression, from other perspective when we have that. So we know that the coefficients, what the coefficients mean by that model. So this is also similar for us. So our model belongs to these models who deliver model-based interpretability. So the shared value among many other, post-analysis, so they belong to interpretable models which deliver post-hoc interpretability. So which in general say that, okay, you don't need to, design some, interpretable model. You can still have a black box model, but we need to open up the black box after we have the model results. So I think shared value is one of them. And I think in economic literature, there are many papers that using so-called importance score to evaluate the importance of different features in some black box models.
Yeah.
So that's kind of the comparison between our approach and the post-hoc approach.
So, and would you have any example of other model-based interpretable methods? You mentioned what was the score? You mentioned.
So, yeah, for model-based. So for model-based interpretable models, I think a nice example is many papers based on tree models. So I think this paper by John Kleinberg et al., which published in one of the top 5 journals in economics, in Quarterly Journal of Economics. So they are an example of a model-based analysis. So because they use a tree model, so it's not a random forest model; it's a tree model. So it delivers the explanation when it delivers outcome. So this is model-based. Yeah.
So do you recall what specific method or approach they incorporated to interpret the random forest?
No, there is not a random forest model. So I guess yeah, this paper is about random forest.
Oh, I see. I'm sorry.
This paper is about is a decision tree type of
decision tree.
Yes.
Okay, I see. Yeah. Okay. I also like when you were describing the persistent change filter. So I understand it replay, or it can replace other statistical methods for actually allocating a structural break in time series. That's correct, right?
Can you say that again?
Yeah. So like previously, because like the persistent change filter works as a method how to identify a structural break.
Yes.
In a time series. So and basically it's a novel method, right? It's because previously there has only been statistical tests to find a structural break or verify there is a break.
Yes. So yeah, this is a good point. So yeah. So our persistent change filter is very relevant to those structure break detection work in time series literature. But we differ from them because we have a explicit functional form. So which is this? So we have an explicit functional form to map a time series into its persistent change filter time series. But as you know, so in time series literature, people mainly focus on developing, some statistics to test whether there is some structural break here or there. So that will not be, very efficient, because if you want to know where the structure break, you need to test everywhere, right? So it's not say you have function and you have some kind of measure of structural break. It's a kind of different. Yeah, I think I would love to add one thing here. So one of the important thing about the interpretable function in general is that it should have some explicit function. It can have a lot of unknown parameters. It can have some unknown parameters, but it should be differentiable. So I think that's the general requirement for this kind of interpretable functions. As you see, those structural break detection statistics, they may not work in this way.
I see. Okay, and if we can stay with the structural change, or with the persistent change filter, you applied it on binary time series, right? But my question, and which basically means when there is a change, it's either by 100% down or up, or there is no change. Can or would persistent change filter work on continuous data that are not limited to not even limited to the interval from 0 to 1?
Yes, actually, so the motivation for us to design this type of functional form is when we look into how we should capture this persistent change in binary time series. But actually, in this paper, we actually use this persistent change filter on continuous time series between 0 and 1.
Oh, I see.
So yeah, it works for both binary time series and a continuous time series.
Yeah. But did you use it as a method to allocate or would it be possible to use this method or inspired method to allocate a structural break, not only to use it in modeling perspective? I mean, would it be possible to somehow develop a method to use it in the same way as we use statistical methods to allocate structural break?
So I guess I think that my screen doesn't work now. So I guess yeah, but I'm happy to take this question. So the persistent change filter is mainly to map one time series to a sensible outcome. So it's not necessarily say we want to find some point, right? So we want to find some interpretable results, but it's not necessarily say we just want to find that structure break point.
I see. Okay. Interesting. I also have a question regarding standard or standard approaches in panel data, because when using a simple regression approach, one may consider to follow the random effects assumption versus fixed effect and assumption, which basically means that individual specific effects are uncorrelated with the independent variable, versus the individual specific effects are correlated with the independent variables. So how can you, or do you see any way how your model can cope with the two different assumptions?
So yeah, this is a very interesting point, because actually we haven't gone that far away, because so when we study individual fixed effect, it is about causal inference, because we want to control some individual to see so when there is a policy change or other things change on this individual, how the outcome would change.
Yes.
Right. So we did not control any individual effect at all in this kind of model, because so we are not want to we're not looking to some changes on a specific individual and see what's a change in the outcome. Yeah, but so for now it's a simple, kind of prediction problem. We just want to know, so who are the employed person, who are the unemployed person, right?
Mm-hmm. Yeah.
So, but in our next step, we are looking into these, causal inference issues. In our next step, we'll definitely consider that in this framework.
Awesome. And would you personally see any other areas or fields where such model can come handy?
Yeah. So for now, this model is kind of a prediction problem. As we know in economics, I think so many people are interested in predictions. So one area is about finance. So if you can correctly predict ups and downs of a stock market, it will definitely be very nice, right? So we are applying this framework in an asset pricing problem right now, and also I think so any people who are interested in the prediction outcomes of their model may find this kind of work useful. And also, if you want to apply this to some causal inference problem, we'll need to further explore how to modify this problem a little bit.
I see. Okay, this have been all the questions from my side. If there is any one question from the online audience you would like to ask, feel free to do it now. Otherwise, thank you, Yucheng, very much for your presentation. It is really amazing work. I really like how you made, or actually how you expanded the toolbox with this model architecture for economists. And what I specifically like is its flexibility. How we can change different functions for the interpretability and also the dimensional reduction techniques we can use inside the architecture. And this is from my side everything. So thank you very much, and I'm looking forward to have you presenting at our spotlight sessions more, again.
Yeah, thank you very much, Jiri, for the very kind invitation. And I'm very happy to talk to you guys today.
Thank you. Good luck.
Yeah, thanks.
Bye.